Perfect. So today, this is chapter 3, and you learned a lot of the concepts that I'm going to cover today in section dynamics. But what we're going to be doing is applying those to biomedical, applications and problems. So we will start by talking about a couple of important concepts in kinetics that they are, handy for biomechanics. And before we do this, we're going to cover what are the common units of measurements. Do you know the common units of SI unit and US custom unit systems? So for Newton and the units, newtons, kilograms, and slug and pounds, we will talk about those. And you did some conversion, right, before. Cool. What are the different types of mechanical loads that act on a human body? We're going to study a lot of the loads. Can you categorize loads in the mechanical loads in? If someone told you types of mechanical loads, what comes to your mind? So tension, compression, bending, torsion. Yes, those are the ones. And you can have a combination of one or more of these, or two or more of those. And the last thing we will talk about the instruments that can be used to use kinetic quantities. Do you remember what are the kinetic quantities that we care about most biomechanics? Kinetic quantities. Force, right, and moment. Those are the ones that we learned about so far. In general, for solid bodies. Now, I'm going to take it a little bit to the next, level, and let's start talking about inertia. How would you define inertia in your words? Not the real definition. Can you explain it to someone who is not an engineer or a physics, resistance to change. That's it. So bodies usually does not like to change their status. So if they're stationary, they want to stay stationary. And if they're moving, they want to continue and stay moving. Now, this is the general physics definition of it. But if you want to look at do you remember something called the moment of inertia from statics? Now, the moment of inertia, so let's say I have these pieces of paper, right? If I'm trying to push on them like this, it will bend, right? Correct? But would it be easier to push it here or this way? So the direction of doing the compression, do you think it's harder this way or this way? This is harder, right? Because the geometry is giving me now more elongation. So this piece of paper is resisting bending based on geometry. And that's the same thing as inertia. But for us in biomedical engineering and biomaterials, we like to look at something called the moment of inertia, not inertia. Does that make sense? And that's something we're going to discuss and talk more about it. So here's what I'm going to do. I'm going to give you some concepts. This inertia is a kinetic quantity, is a kinetic parameter. But we care about moment of inertia, not the inertia. And we sometimes call the area moment of inertia or the second moment of inertia. But we'll discuss this later on. So in physics, from physics, inertia is the tendency of a body to resist change in its state of motion. So if the object, stationary wants to stay stationary, if it's moving, wants to stay moving, directly proportional to mass. Now that is the important part. Your inertia, resistance to motion, is directly proportional to mass. What does that mean? If mass goes up, what happened to inertia? Goes up, correct? That's the directly proportional. Now, it has no units. Now, here's the thing. For the moment, the inertia, can you give me an example that can, or explain to someone effect of inertia based on mass in sport? In sport, with big mass, if they try to move because of them. Yeah. So what do you do? Do you call this move you do the tackle? That's the tackle, right? So if someone has a bigger mass, it's harder to move, and that's how we use inertia. It has nothing to do with muscles. It's just the mass. Muscles will be good. It's always important, but the mass itself makes a big difference in inertia. Does it make sense? Also in basketball, larger inertia in basketball or mass in basketball help player to resist offensive. So if someone is pushing on them or with their body, they're not going to touch them. Otherwise, they will have a foul, right? So that's another application of mass in doing that, and that's the reason why you will find. My assumption is that you will find divers. They have smaller mass because they want to move quickly and they don't want to have anything that is stopping them. And then we're going to talk about how changing body position will affect the movement. Does it make sense? And it has no units. So inertia has no units. But it is the key point here. It's directly proportional to mass. The larger the mass, the larger the inertia of the object. Cool. This is a cool cartoon. The weight bar will stay in place in the absence of being lifted because of its inertia. And inertia is related to mass, and we have established that. We good? That's your first kinetic parameter that is related to mass that we need to keep in mind when we study biomechanics. Now, we talked about mass. So how would you define mass to someone who is not knowledgeable in, the basic physics? What would you say? What would you say to him or her mass is? Yes, material. Yep, that's it. And if you want to define it, it's the quantity of matter. It's the material. How much matter do we have? And composing a body. And examples, those are, objects. But here's the thing. Till now, you have learned to deal with mass as it is concentrated in a point, correct? Physical, sphere, like a point mass. We call it point masses. Does that make sense? That's a point mass for an independent, separated object. Does that make sense? We're good with that? Now, and it's represented by M, and the unit in the SI in the international system is kilograms. We good? Make sense? Now, what is mass in the US custom? Slug. Thank you. So it's a slug in the SI in the US custom system. Now, masses, as I told you, you learned how to deal with a mass if it is a mass point. Now, here's what happened. In biomechanics, we're not dealing with mass point, correct? We have segments, and we have segments like upper and lower extremity segments, and these segments, they do have distributed masses. So the difference between a point mass and distributed mass, something like this. Here's what happened. This is supposed to be a deer, okay? And we have a rule. We are doing biomechanics. Your job is to simplify structures, correct? This simplification is called, it has a name, it's called idealization. Now, I'm idealizing a body with weightless segments and mass points placed on specific locations on the segments. Does it make sense? Right? So the first step or task you need to do if you want to study any motor task is to idealize the structure. Then you need to construct the equations of motion. And we have two ways. We have the Newton force approach, and we have the Lagrange energy approach. And the third thing is to solve the equations of motion. And then you can say that you are doing human motion analysis. Now, in this class, we care only about the structure, which is idealization. In your rehabilitation engineering class, we will talk about constructing and solving the equations of motion. But what I want from you to see that this is not an independent one object. You have multi-segment coupled pendulum system, and you have masses on it. Now, how could I deal with this? We need to come up with something called the relation matrix that tells me how are the masses distributed on the body. Remember, the segments are weightless, so they don't contribute to motion. Remember inertia? Inertia is proportional to mass. So the thing that contributes to the motion is the mass, and it has the velocity. So I'm going to work with you on this example. I'm going to construct with you something called the relation matrix, and I will construct with you the generalized mass matrix, because I'm not going to look at one mass, right? Because I have multiple masses now on the system in the system. So here's what I'm going to do. This is a two-dimensional system. How many segments do we have? See white circle? This is a joint. So 1, 2, 3, 4, 5 segments. Right? You're going to do this. We're going to do this exercise together, but I'm going to represent the human, this structure first, and then we'll do that. So I have 5 segments. How many mass points do I have? The black circles are the mass points. 1, 2, 3, 4, 5, 6. We would like to learn, can I represent this in a matrix format? So if I give you the matrix, you can rebuild this, or if I give you this, you can make the matrix. And we'll call this matrix a relation matrix. It is representing the connections between the segments and where the mass points are. Remember, we are not working with a single mass. We have now multiple masses for our system. So what I will do now, each mass should have a row, and each segment should have a column. So this R matrix here, see this R? How many masses do I have? 1, 2, 3, 4, 5, 6. I will have 1, 2, 3, 4, 5, 6 rows. 5 segments, 1, 2, 3, 4, 5 columns. You have one rule. You cannot have a segment that's connected to another, to make a closed loop. So your upper extremities, none of them is connected to make a closed loop, right? You can't have this and make the subject move. It's impossible. So all segments should be free, no closed loops. Now, this is the first segment. I'm going to identify an origin as 0, 0, 0 point first, before I do anything. And then I will construct my relation matrix from that point. Here's what I'm going to do. What we care about is the masses, correct? Because those are the ones going to make the movement. How far mass 1 is away from the origin is Z1, correct? So let's say this is 10, this is probably 8 or 7, right? So I will put the first row, the distance of the first mass is Z1. Now, what is my second mass? This is second mass. How can I reach that mass? I will go the entire L1, right? Then Z2. So that's L1, Z2. So each row is for one mass. Mass 1 to get to mass 1 from the origin, I need to go Z1. That's your Z1. If I want to reach mass 2, it's L1 and then Z2. How do I reach mass 3? It's L1, L2, Z3. Does that make sense? Right? Now, I have to go to the other branch. To get to the first mass in the M41, which is the mass 4 on the first one, I have two masses on this segment. The first mass. I need to go L1. Do I have L2 or L3 connected to it? No. You'll have 0, 0. And then you have to go Z41. That's what you put this for. Same thing for the second mass. L1. Do I have any of the other two? No. 0, 0. And I'm going Z42. That's the distance. And then if I want to go to M5, I have L1. Do I have L2, L3? No. I have all L4 and then Z5. Remember, all of these are lengths. And this way, if I hide the structure, you should be able to build it from this relation matrix. Because you know how many masses do you have, you know how many segments, you know which one is connected to which, and you build that. Does that make sense? Now, in order to have, this is the relation matrix. So this is how the system is connected. You as an engineer, you will be building the structure for the body. Now, if you want to have the generalized mass matrix, we can do something called, we need to have a diagonal mass matrix. So how many masses do I have? 6, right? M1, 0, 0, 0, 0, 0. And then, the diagonal matrix, I'll put the masses on the diagonal and everything else is 0. And then you'll have M2, right? 0, 0, 0, 0. And at the end, you'll have 0, 0, 0, 0, 0. That's, let's say 5, because you have two 4s, M5, right? So that's a 6 by 6 matrix, diagonal matrix. You multiply, do you know what's a transpose? Rows will become columns and columns becomes rows. So you take R matrix, do the transpose of R, multiply by this diagonal matrix, then by another R. This is called the generalized mass matrix. So if in biomechanics, instead of using one mass unit of one value for one mass, I'm going to use this to do the analysis. Because I have now a lot of segments connected to each other. And that's called the generalized mass matrix. Okay? Now, let's do it together. Let's see how that's going to work. I printed, this is a publication from 1964. It's an awesome publication. And you have a copy of the whole thing. It's like a journal. You have a copy of it in week 2 for you. But I printed also copies to give to you. So here's what I want you to do. I want you to look. So those people, those guys, 3 fellows here, they spent, the paper is long. You have just a small portion of that paper. So they looked at the human body and they tried to characterize the lengths and mass points. And they used 2 different ways to do this. We're not going to go into the details, but I want from you to go into the page. Table 1, see table 1? This is the absolute and relative lengths of body segments, right? So head and neck, and you have G and K. G and K, they're 2 subjects, just they're hiding their information. And the data is reported in centimeters. So centimeter, you divide it by 100, you get a meter, right? And that's an SI unit. Now, the next side is the relative. So the first, 1, 2 are absolute values. Column 3 and 4, so 3 and 4 for the length of the same subject, but it's normalized to the hand length. Because people were saying, I don't want you to give me how long is your hand in centimeters or your arm in centimeters. Can you give me your arm length relative to how much your hand? Just to normalize it, to be consistent. Because if you have a longer arm compared to me, and I'm comparing things between you and me, it's not going to be consistent. You need to normalize it to something. So people usually they normalize it to the length of the hand or the length of the entire body, which means dividing it by the length of the entire body. Okay, so table 1 is the length. Table 2 is the absolute weight of the body, the masses. And you can see this figure here. That's how the masses were distributed in the body. So you will have the head, the upper, this is the head mass. This is the upper trunk mass. This is the lower trunk mass, right? I want you to be split into 2 groups, left and right. Group 1, I want you to select this point to be your origin, and I want you to find the relation matrix for the left arm. Group 2, I want you to select the upper extremity. I want you to select the hip to be your 0, 0, 0 point, and I want you to find the relation matrix for the left leg. This. Make sense? Now, here's what I want you to do. I want you to fill R, M, and the diagonal one, and the other R, and to just construct the generalized mass matrix for each system. Make sense? This is a group work, so I want you to work together. And I want to have matrices with numbers, not with just M1, M2, M3. And you get the numbers from the tables, right? Make sense?
Use the boards?
Yep. But I want to give you papers because I want to have those uploaded to the D2L. That's in class activity. Let me give you papers. Okay, so this is an exercise where we're going to be applying this generalized mass matrix just to have a practice to keep in mind. We are no longer dealing with independent, separated masses, individual or same masses. We're doing the left, and I want you to put the 0, 0 here, right? That's your 0, 0. Okay, we will have 5 minutes. Okay, let's do it 10 minutes. Oh, I changed my mind. I want you to do it the right leg because the mass on the foot is in the middle. There is a reason why that thing is on the ankle. But we're not going to go for that. Do the right leg. Sorry. And still, the hip is your 0, 0, 0 point.
0, 0.
The hip. Yeah, the white circles are. Were you able to get the mass? Okay, guys, you need to upload your work and to a Dropbox, and let me just finish this, and I will create the Dropbox. You can have this until next time we meet, and then I will review it with you just to make sure that you have that. But I need to move to the next exercise because that's another important thing we need to make sure that we are aware of. I think that is, that's great. Okay, we'll take 1 minute. And then we'll jump to the next. Yes, you need to divide by 1,000. So always in our units, make sure that you have meters, kilograms, or pounds, and you don't have to have fractions. This is useful, right? Oh, the exams, but not the quizzes. But I'm not sure how we're going to be putting it in an exam. If I want that in an exam, I will give you the structure with all the length and disease on it. But going through this exercise. It took a long time. Yeah, okay, guys. Can we move to the next topic, or need more time? We good? And the take-home message actually, when you read any publication or a book for biomechanics, you will not find absolute lengths and values. All of them are normalized. Does it make sense? And are we good that we are normalizing either to the hand or to the length of the body? The standard now, this is 1964. The standard now is you normalize only to the body length. Are we good? The standard now is to normalize to the body length, not to the hand. Okay, can we move on to the next one? Okay, so we talked about inertia. We talked about masses. Now the masses will be moving. And as they move, we will need to look at forces. And that's what you covered in statics. So how would you define a force? it's the push or pull acting on a body. That's the definition of the force. And because it's a vector, remember the force is a vector, and we need to have magnitude, direction, and there's another important aspect in biomechanics, which is the point of action. You see this skeleton? What is the connection between bone and muscle called? What is that tissue? It's the tendon. So the point of insertion of tendons on our skeleton are the point of action of the forces. Does that make sense? Are we good with that? And that's why when you look at this figure here, see where the upper arm and the lower arm, see where the muscle is connected to the bone? That is what is your point of action. So we need to make sure that we understand that, and we're going to come and do some analysis with the body. Now, remember statics and dynamics, measuring or finding the resultant force, finding the moment. We're going to do this for the human body. Now, force is mass times acceleration, correct? What's the unit of mass? Kilogram. And acceleration per second square. So if you multiply kilograms by meters per second square, that's your Newton. That's the unit of a force. What is the unit of force in SI unit, in the custom US system? Pounds. Pound is the force in the SI unit, right? In the US custom unit system, it's pound. Okay. Now, forces, in order to be able to analyze forces in the body, we need to look at muscles. Do we agree? The points of action of the muscles are where the tendons are connected to the bone. Do we agree? Right? Good. Now, next step, before we do any analysis for forces, we need to create something called the free body diagram. Do you remember that? And in statics, you learn about acting forces, right? External forces. And we have something called internal forces. You remember trusses? It's a tough one, I know. There are internal forces. When you cut this, you have internal forces. And then we have something called friction force. In the human body, we're not going to cut anything. So we don't care about internal forces. It's all external forces and friction. So a free body diagram is a sketch of the system being analyzed and vector representation of the acting force. So if this is a ball, you have applied force by the racket. If it's a tennis ball, you have air resistance and you have the weight of the ball. You'll do all of those. Now, forces in the human body, the most important part of the body to identify the forces on, which one is that? Which part of our body we need to make sure that we know the forces on that part? It's multiple. It's the joints. You need to find the net forces or the free body diagrams on the joints. Does it make sense? And that's why the joints, because you have a lot of muscles connected to the joint, close to the joints, and they are acting on the movement. Now, here's the thing. Do you remember the names of the angles we use to analyze static systems? How many types of angles do we have? So what do you call the angle, these shaded angles? Those are called projection angles. We have another type of angles. Do you remember the coordinate angles? It's the angle between the line of action of the force and one of the coordinates, X or Y or Z. So we have two types of angles. Anything shaded, projection angle. Anything that is between a line of action and the axis is a coordinate axis, right? Coordinate angle. Now, the net force is the summation of all forces on a specific point, right? So if I have, it's a single resultant force derived from the composition of all acting forces, the force that determines the net effect on the all acting forces. When all acting forces are balanced or cancel each other, the net force is 0. That's something we learned about before. Now, I have an example. We have 5 minutes. Let's see if we can finish this example in 5 minutes. It's a refresher about how do you analyze, how can you find a net resultant force, because that's important when we want to analyze the forces on the joints. Quickly, let me show you something. You did something like that. Tell me the coordinate angles. With the x-axis, what is that angle? 120. The one with the z-axis, 60. How many projection angles do I have? 2. They are all for F1. Do you remember how do we decompose or deconstruct each vector into its component, x, y, and z, I, j, k? So the first one here, if I want to analyze, before I find the resultant between F1 and F2, I need to break each one of them into x, y, and z components. That's what we did in statics. How would I do the analysis of F1? You want, so this is 35 with the z-axis. What I will do, I will create an imaginary z-axis here, and I will say that this is F1. What do you think? Is it cosine or sine 35? Cosine is always with the axis that have the angle. The sine is the one without the angle. So that's going to be sine 35, correct? And then I will create another force here. I'm trying to analyze F1. I'm going to call this F prime. And this F prime is going, F1 prime, is going to be F1 cosine 35, correct? I don't need this, that's gone. Now, this one here need to be projected on the x and y. So, and I have with the y-axis 25. So I can say that this here is F prime 1 cosine 25. And that equals F1 cosine 35 multiplied by cosine 25. So I did this force, if it has projection angles, I do it on 2 steps. One step with the z, and then the other one on the plane, and then that you do the projection on the other sides. And this one here on the x-axis is going to be F1 sine 25, and you don't need F1 prime sine, and you don't need that one. So I have now 1, 2, 3 components on each side, and that's going to be F1 cosine 35 sine 35. So two types of projections. So if I want to do it here, show it to you with more details. See this F1, I made the Fz, which is this one here, same one here, and then F prime, and then the F prime, I projected it on the x and y. So F1z, why do we have it negative? It's going down, right? And the F prime is 25, F1 is 250 cosine 35, that's the newtons. And if you do the other projections with the x and y, your F1 will look like this: 85.6, 185, and minus 143. So that's how I decompose a force with projection angles. You good? Now, the other one here, the other force, F2. F2 is easy because we can use the cosine rule. If you have coordinate angles, you can do this. The x component is 400 multiplied by cosine the angle with the x-axis. 400 with cosine 45 give you the y component, and 400 with cosine 60 give you the z component. So I have all of, it's very easy to get the coordinate angle. It's the projection that takes time for us to do that. So you have F1 in xijk, you have F2 in ijk, you add them together, right? You get the resultant force. And that's what we're going to be analyzing with for the human body. You will have multiple muscles acting on a joint, and we need to find the resultant force on that joint. And we're going to solve problems together on that. But this is a quick, review. Now, the resultant, do I know the direction of this force? I can draw it, but I need angles. Do you remember we can find the angles of with the coordinate angles using also the cosine inverse rule? Do you remember how we find the magnitude of this force, Fr? So Fr, go ahead, Ethan. So you take minus 113 square plus 468 square. So that's the magnitude, plus 56 square. I didn't do the, decimal, but that's fine. Now, if you have the magnitude and you have each component, I can find the angle with the x-axis by saying, give me cosine inverse, this value divided by the magnitude of the vector itself, the entire magnitude, and keep the signs. So you can find for alpha, this is alpha, which is the angle with the x-axis, beta angle with the y-axis, and gamma is the angle with the z-axis. Take the x component divided by the magnitude that we have as, 485. Take the cosine inverse. Those are your angles. So now I know the resultant and the angles, the direction of it. That's a quick refresher about how we do the resultant force and what kind of angles, because the angles are important. We have projection angles, we have coordinate angles. Now, someone mentioned the center of gravity, Alyssa, right? Now, the center of gravity is where all the forces of your body equals to 0, and if you change your position, that center of mass changes. And if you have a ring, let's say, of metal, the center of mass does not have to be on the metal. It can be in the middle with the emptiness. So this is, see my ring here? The center of mass is in the middle. It does not have to be on the mass itself. So you can do this, and your center of mass is outside of your body. You can tilt to the one side and you mass it out. And that's all what I wanted to cover. I know I went quickly through the example, but if you want to go back to it next time, I will do that. We good? Enjoy your long weekend, and hopefully that was useful 2 weeks so far. Thank you so much, and I will see you on Wednesday.